Calc 2, lecture 33, infinite sequences and series, and we are in the section of alternating series. Now, a series of the form, this form, sigma n from 1 to infinity, minus 1 to power n minus 1 bn is called an alternating series. And why? If I write this, let's say expanded, I have b1 minus b2 plus b3 minus b4 and so on. And you can see that the sign alternates. Now we make this assumption that the bn is bigger than or equal to 0. So if bn is negative, say, then this negative can be multiplied by this negative 1. So that's negative 1 times negative 1. And you will get negative 1 to power n. So this can be either n minus 1 or n depending on the starting point. So if the first one is negative, then you have this. If the first one is positive, you have this. But most often we have, we start like this because we start with a positive term than a negative term. So, now, well, this is the form that we had before for infinite series. Usually n starting at 1, going to infinity, an. If I compare this with what I have here, then an is in fact this. This whole thing is an. So the general term is minus 1 to power n minus 1 times bn. And again, I emphasize that we assume that bn is non-negative. Okay, now the alternating series test, which is quite useful because many interesting functions, important functions like sine and cosine, they have alternating series expansion. We will see that in power series. So that is the alternating series test. So that's the theorem. That's alternating. Test. Alternating series test, and which we abbreviate AST. Alternating series test. So, sigma, let's start with, it doesn't make any difference if we have n minus 1 or an, or n, sorry, is convergent if a bn is a decreasing sequence and v limit of bn as n goes to infinity is 0. Okay, so if you have an alternating series satisfying these two, then it is convergent. So that's alternating series test. Now let's start with examples. I'm not going to prove this thing. There's some kind of proof in the book, and the proof needs more advanced ideas of mathematical analysis. So let's let's just give you examples here. In fact, yeah, I think we can prove it using the comparison test, but the comparison test itself needs more mathematics. Okay, so examples. Now from here, sigma n from 1 to infinity minus 1 n minus 1, 1 over n to power p is convergent for any p bigger than 0. And this might be a surprise to you because if it's not alternating, it depends on p. But when it's alternating, no matter what p is, it is convergent. Why? Because Let's look. AN or BN, this is the BN. This is my BN. Okay, BN, which is 1 over n to power p, is decreasing. We can look at this, so Bn plus 1 should be less than Bn. So let's ask this question, is this less than Bn? So let's check. So check is, that is 1 over n plus 1 to power p. Is this less than 1 over np? Yes, because 1 over n plus 1 is less than 1 over n. Now raise it to any power, that doesn't change. If the power is bigger than 0, that doesn't change this inequality. So I have A and the B limit as n goes to infinity of 1 over n to power p. Just look, whatever this p is, you might say this p might be 0.000001, something very small. But this n goes to infinity. Eventually the denominator is infinite. So 1 over infinite is 0. So this limit is also 0. Okay, so because the two conditions apply, so this, because by, also this implies that by alternating series test, that sigma minus 1 to power n minus 1 Bn is convergent, right? So for alternating series, if you want to prove that it is convergent, you have to check these two. You don't really have to show this one, for example, but it's okay since you have enough time if there's an exam or something. So it's better to show this. So let me erase this on top and discuss this thing here. So we have 1 over n plus 1 is less than 1 over n. Why does this happen? Just cross multiply, because n is less than 1, is less than n plus 1, right? Is less than n plus 1. So if I find the reciprocal, this changes, right? So the reciprocal is 1 over n, and is bigger than 1 over n plus 1. That's because they are positive. So if I raise it to any power, p bigger than 0, then this inequality holds. But this is in fact 1 over n plus 1 to power p and 1 over n. Okay, so that's what happens. That's why this is true. And this one we know is true. So by the alternating series test, AST, any series of this form is. Now, since I have not, let me still keep this because there is a word of caution here, and I have seen students doing this. If you do that, I will not fool you. So, what is it? When students, so mistake, and let's say big mistake, they keep that negative 1 to power n minus 1. Don't drop, big mistake. So they keep that. They write something like this. N is decreasing. Wrong. Don't keep this negative 1 to the power n minus 1. Or, for this one is okay. If you write negative 1 to the power n minus 1 in front of this, it's still 0. But this doesn't apply to the first one. You have to drop the negative 1 to the power n minus 1 and keep just Bn. And assuming that Bn is in fact a positive or a non-negative number. So, please drop the n minus 1. So I mean minus 1. 1 to power n minus 1. So please drop that. Please drop this thing. Okay, so you have to show that Bn is decreasing, not minus 1 and minus 1 Bn. B, limit of Bn as n goes to infinity is 0, not limit of n goes to infinity of negative 1 and minus 1 Bn. Okay? So drop the negative 1 to power n minus 1. Okay, so that was the. Now, as special case, let's analyze the harmonic series. So harmonic series. And alternating harmonic series. So harmonic series was this: 1 over n, and from 1 to infinity, divergent. This one, sigma, minus 1, n minus 1, and from 1 to infinity, 1 over n, convergent. Okay, so these are the two, this is one of the most important examples. Again, we are back to the harmonic series, 1 over n, and we see by the theorem that this one is convergent. Now you can now say, if I look at this, let's use intuition. This is 1 plus 1/2 plus 1/3 plus 1/4 plus that. What is this? 1 minus 1/2 plus 1/3 minus 1/4. You can see that this is 1/2. Then it's added to 1/3. Then again 1/4 is subtracted. So we have some positive terms and some negative terms. And the negative terms, in fact, cancel the effect of the positive terms. So, but here it's all positive. They're all added. But here they just cancel. They cancel each other to some extent, not completely. And you can see as n gets larger and larger, they are really the same. So 1 over 10 million minus 1 over 10 million and 1, they're almost the same. Basically, they cancel each other. So as n gets larger and larger, then this and this say they really cancel each other. They cancel each other. Well, I don't know which one is negative, which one is positive, but as n gets larger, this becomes 0 almost. As n gets larger, you can see that as n goes to infinity, this is 0, this is 0. 0 minus 0 is 0, right? So as n gets larger and larger, the two consecutive ones, the result of adding them, which is not adding, it's subtraction. Each two of them at some point, they just cancel each other. So this basically goes up to some point. Then after that, what we are adding to this Sn, the partial sum, is basically a small number, and it gets smaller and smaller and smaller. So small that it basically vanishes. So that's the big difference, right? This is all adding, this is add, subtract, add, subtract, add, subtract, and so on. Okay. Now let's look at the residue or the error. So if I let S be sigma minus 1 and minus 1 be n, and n from 1 to infinity. Well, let's write k, right? Because I made n. So let's use k. So somebody was asking me about this, and I didn't understand exactly what they were saying, but this k is what we call a dummy variable. So it can be n, it can be m, it can be I, or anything. So that's the sum, and Sn will be, say, sigma k from 1 to n minus 1k minus 1 bk. You see why I used k here. Now, what is S minus Sn? Right? So what is S minus Sn? So if I write this, this will be absolute value. So this is sigma k from 1. In fact, it starts at n plus 1 and goes to infinity, minus 1 to power k minus 1 bk. Right? And you see that this is basically getting smaller and smaller. And I emphasize that you see, as this gets larger and larger, I have, say, bn minus 1, then I have a bn. And they get closer and closer to each other. Why do they get closer? Because this is a decreasing sequence, and also its limit is 0. So this becomes almost 0. So that's one way to show that this Sn approaches something. Now, the error is this. Let me use this fact here to come up. Okay, let's see. So that is the estimation theorem. Alternate is the estimation theorem. So yeah, that's what it's called. Alternating series. Okay. So it's saying that this, in this situation, since we have a, b n plus 1 is less than or equal to bn, and b we have limit of bn going to 0 as n goes to infinity, then this s over sn, s minus sn, becomes less than or equal to bn plus 1. So this s minus sn, which is this thing, and we call it Rn, this becomes less than or equal to bn plus 1. Okay? So, that is in fact the alternating series estimation theorem, and it's not hard to prove that. So, let me first give you some examples of this thing, and how this thing is used. Then give you some ideas how this thing is in fact proved. So examples then, first examples. Examples of, say, using our so Rn, which was S minus Sn, we proved that it is less than Bn plus 1. And remember, the Bn's are positive. So Bn plus 1 is a positive number. Okay, now, let's say sigma minus 1 n minus 1 n from 1 to infinity Bn. So if I find n, or find n such that S minus Sn is less than 10 to the power negative, say, 9. Okay? So we want the error to be less than 10 to the power negative 9. And we need to know how many terms to use to get to this point. Okay, so by this theorem we have S minus Sn is less than or equal to Bn plus 1. So if this is less than or equal to 10 to the power negative 9, then we're done. So we basically write this, and this is less than Bn plus 1. And if this is less than 10 to the power negative 9, then this is less than 10 to the power negative 9. So we have to find n. But so we have to solve this inequality for n. Bn plus 1 less than 10 to the negative 1. Solve for n. Okay? So we have to solve this inequality for n. So let's let me erase this and solve the inequality for n. What is Bn plus 1? Where is it? There. Oh, yeah, that was I'm using it for, let's say, let's apply it to negative 1 to the power n minus 1 bar over n. Sorry, so I just let go B. So here, B n plus 1 is simply 1 over n plus 1. So we want 1 over n plus 1 to be smaller than 10 to the power negative 9. So if I flip this thing, this is n plus 1 should be bigger than or equal to 10 to the power 9. And this gives me n should be bigger than 10 to the power 9 minus 1. So n is basically bigger than or equal to how many? Well, that's just 9. How many 9s do I have? Well, whatever. So that is 10 to the power 9 minus 1. So that's a huge number. That is a huge number. 10 to the power 9 is this. Let me erase this. 10 to the power 9 is, in fact, this. 10 to the power 9 is 1, 2, 3, 4, 5, 6, 7, 8, 9. And minus 1 will be 1, 2, 3, 4, 5, 6, 7, 8, 9. So this n should be bigger than or equal to this. So if so S minus, in fact, sigma, say n starting at 1, going to this number, 1, 2, 3, 4, 5, 6, 7, 8, 9, and negative 1 to the power n minus 1, 1 over n. This will be less than or equal to 10 to the power negative 9. That's the meaning. So, and you can see that this is a huge number. I mean, you have to write a loop, a computer program with a loop that goes from 1 to, what is this thing? 1,000, a million, is it trillion? Something. I don't know. It's something. So, that's a lot. That is a huge. So just imagine this is 10 to the power negative 9. If I wanted 10 to the power negative 20, say, then I had 20 9s here, and from 1 to that number, That's just huge. So one can say that although this series is convergent, but it seems it doesn't converge so quickly. That's what we mean by quick convergence. So let's check another one. Let's check 1 over n to power, say 2, okay? Just one extra. Then this is n plus 1 squared. Then this n plus 1 squared will give me n plus 1 squared bigger than this. And this gives me n plus 1. Well, that's okay. So it is bigger than 10 to power 9 over 2. And this gives me n is bigger than equal to 10 to power 9 over 2 minus 1. So what is 10 to the power 9 over 2? Well, let me calculate this for you. And minus 1, 10 to the power uh, 3162.1.8. So that's 3, 1, well, it's not exact, 31621 almost. So I would say bigger than 31622, okay? So it should be bigger than equal to this number, and that's 0.8, right? So that is 31622. Okay? So that's n squared. So for n 1 over n squared, I need 31,622. For n, I had like in trillions or something, right? So you can even check, let's check n to the power 3, n3, and you see how n3 works. So if I have n3 here, then I have n3 here, then I have n3 here, then I have n3 here, and this one. So here I have n to the power n over 3, which is 3 in fact. So that is 3 minus 1, which is, this one is exact. So this will be 1000, right? So that's 999. And this will be 999. And this is 3. That's it. So you see, this one converges, as we say, convergence much faster than 1 over n. 1 over n is just terrible. You can imagine if I had the 1 over n to the power 1/2, say. That's convergent, but again, you need maybe even, I don't know how much larger than that. That would be, so I guess that's 18, yeah, that would be 18 nines. Anyway, so that is how this thing is used. So you are given something, and they say, okay, find an n such that the approximation is good up to certain error. So they give you the error as 10 to the power something, then they ask you to find this n, for which s minus sn is less than that. Okay, now. Another thing here is well, let me check and see what else do I have here. No, not too much here. So that was in fact the alternating series test. And as I mentioned, there are so many amazingly interesting power series which are alternating. Let me say sine x, for example, is x minus x3 over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, and it continues. So that's alternating. Cosine x is in fact alternating 1 minus x squared over 2 factorial plus x 4 over 4 factorial minus x6 over 6 factorial and plus minus. So these are alternating, but e to the power x is not alternating. So there are in fact amazingly nice alternating series. Okay, so next time I will go through something else and hopefully get to power series quickly. And okay, so see you next time.